All right. Hi folks. So now we're really going to calculate the enthalpy of the combustion of methane, and we'll do it via bond energies first, then we'll do it all again using Hess's law. So bond energies, we have to first write a balanced chemical equation. So combustion of methane, remember that combustion always starts with the chemical, right, methane, for example in this one, and we need to remember to put our phases in at this point in the year. So methane is a gas. Now combustion always has one more reactant. If it's complete combustion, there'll be an excess of oxygen gas. And our products will always be the same too in a complete combustion. So carbon dioxide gas and water vapor gas. That's a gas. Okay, so now, is it balanced? Well, I know it is not. So we've got 4 hydrogens here. If I do this, I'll have 4 hydrogens here. Now I've got 2 oxygens here and 2 here for a total of 4. So now I've got 4 oxygens there, 1 carbon, and so we're all balanced. So that will do. Now when you do bond energies, you need a Lewis structure for every reactant and every product. CH4 is just easy like this. And you can do Lewis dots if you need to look at where the electrons go. Oxygen, you know oxygen has 6 electrons. So there'll be 12 total electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe I'll move that guy down. So we'll have a double bond. Now double bonds, of course, contain more energy. Enthalpy, energy stored in the chemical bonds. Potential energy stored in the chemical bonds. So the double bond will have more than if it were like oxygen single bonded to oxygen, right? But of course we know that we will basically ignore this because this is oxygen's elemental form, so it will be 0. If it were another double bond, like if one of these were double bonded, it would be significant. But that's a rule, by the way. Oh, I have a baby. Eek.
Hello, Mommy.
Hi, go to Granddad. The energy stored in the elemental form. Any element. Yes, go. The energy stored in an elemental form of something is always 0 for Hess's law. So since oxygen is a homonuclear diatomic, O2 is its elemental form, so it is going to have an enthalpy of 0, standard enthalpy of formation of 0. Oh goodness, little buddy. Thank you. So then carbon dioxide. We've got a carbon with 4 electrons. Oxygen will have 6. Oh, where can I put them? I'll put one here and one here, I guess. 1, 2, 3, 4, 5, 6. So this bond here will become a double bond. Then 1, 2, 3, 4, 5, 6. This will become a double bond. So we'll really end up with C double bonded to O, double bonded to O, like that. And of course the CO double bonds will contain more energy than a C single bond O. And H2O, of course, you all know. So we'll have these bonds. Then what you'll need is table 13.1. I'll give you this nice copy for the test. So we'll have 4 of these CH bonds over here. Well, and we'll need an equation. So let's see. The bond energy equation, remember, is backward from Hess's law and all the other equations. So it's going to say, my old brain has to work, of course. Hess's law says products first. So this will be reactants first. The enthalpy will be change in enthalpy of, can't even remember what I just said. Reactants minus change in enthalpy of products. So we'll look at the reactants first, these. So to find the answer here, I'm going to say I have 4 CH bonds. So 4, and in fact I'll just call them moles of CH bonds. So I look right here, I see a CH bond has a bond energy of 411 kilojoules per mole. And I have 1, 2, 3, 4 moles of bonds because there are 4 CH bonds in each molecule of methane. So 4 moles of bonds, even though it's one molecule, times 411 kilojoules per mole. That's my first reactant, and it's actually kind of good to use a bracket to surround the reactants and another bracket to surround the products so you really keep them straight. So you add up the sum of the reactants, actually the whole equation, it has like sums here. So you add up all the reactants and you add up all the products. So reactants, other reactant is oxygen, oxygen, double bond. Oh, and bond energy, oh, it does matter, bond energy, it just doesn't matter in Hess's law. So 494 kilojoules per mole, and there is only 1 mole of bonds, 1 bond. Oh, but there are 2. So we've got a 2 here in the balanced equation. So times 2 moles. So this whole big thing here, because of the balance equation, this is just the reactants. But now subtract and come down to the next line for the products because it's too long for my board. So products, I've got carbon dioxide, just 1 mole in the balanced equation, but I've got a CO double bond here and a CO double bond here, effectively 2 moles of bonds. 2 moles times, and if I look on the chart, the CO double bond, 799 kilojoules per mole. Ooh, don't close bracket yet. Plus H2O, and this is a gas. Remember, bond energies doesn't consider the phase. It doesn't matter if it's a gas, which is why it's slightly inaccurate. So we've got 2 moles here and 2 sets of bonds here. So effectively 4 moles of OH single bond. So I look here, OH single bond, 459 kilojoules. So I got 4 moles of bonds, 2 in the balance equation, times the 2 because there's 2 bonds in each molecule, times 459 kilojoules per mole for a OH single bond. Alright, then I close my bracket. So I've got all the reactants here, all the products here. Then I put that into my calculator, and I find 4 times 411 to be 1644. Of course my mole cancels and I get kilojoules. So then 494 times 2, 988 kilojoules. Remember, joule is just an energy unit, nothing scary. Then I subtract, because it's the reactants minus the products, and I keep my brackets here. 799 times 2 is 1598 kilojoules, and add that to 4 times 459. 1836 kilojoules. Alright, so add them up, 1644 plus 988. Everybody has significance to the ones place, so we can keep a ones place everywhere. So this is 2632 minus 1598 plus 1836. 3434, both in kilojoules. Kilojoules. Okay, so then 2632. Okay, so I get negative 802 kilojoules for bond energies for the combustion of methane. So if that's confusing to you, you can review it. Hopefully I can do like one more problem for a video. I'm going to stop this video and come back and do another video with calculating exactly the same thing using Hess's law instead of bond energies. Should get a similar answer because it's the same problem, but Hess's law is more accurate and the test asks you why, so be very clear about why. I'm not considering with bond energies the phase. It doesn't matter that these guys are gases, because a gas will have a slightly larger amount of energy stored in its bonds than a liquid or a solid, but bond energy doesn't take that into account. It just uses a standard set of tables regardless of the phase, so it's not going to be quite as accurate, but as you'll see in a minute, we'll get a pretty close answer. It's a pretty decent way to do things if you don't have the ability to use Hess's law, if you don't know the phases, for example. So I'll be right back with the next video.